Nuclear energy is more than just a means of generating electricity. It has far-reaching applications in various fields, improving our lives in countless ways. Radioisotopes, produced in nuclear reactors, are indispensable tools in medicine, used in the diagnosis and treatment of various diseases, including cancer. Agriculture also benefits from nuclear technology. Radioisotopes are used to develop disease-resistant crops and enhance crop yields, contributing to global food security. The heat generated by nuclear reactors finds applications in industrial processes, such as desalination, converting seawater into fresh water to address water scarcity. The potential of nuclear energy extends beyond our planet. As we venture further into space, nuclear power emerges as a reliable and long-lasting energy source for spacecraft and future lunar or Martian outposts. Its high energy density and compact size make it ideal for powering long-duration missions, enabling us to explore the cosmos like never before. Despite its immense potential, nuclear energy has faced challenges and scrutiny. Public perception has been shaped by historical incidents, raising concerns about safety and waste disposal. However, the nuclear industry has made significant strides in enhancing reactor safety, implementing rigorous regulations, and developing advanced technologies. We will delve into the intricate workings of different reactor types, from the widely used pressurized water reactors to the innovative small modular reactors that offer enhanced safety and flexibility. We will explore the rigorous safety measures in place, including emergency shutdown systems and containment structures designed to prevent the release of radioactive materials. Join us on this captivating journey as we unravel the mysteries of nuclear energy, exploring its past, present, and its promising future. Together, let's delve into the heart of the atom and discover the transformative power it holds for humanity. Imagine a force so potent that it can power entire cities from a source no larger than a house. This is the allure of nuclear energy, a testament to humanity's ability to harness the fundamental forces of the universe. At its heart lies the nuclear reactor, a technological marvel where the very essence of matter is transformed into a torrent of energy. Unlike conventional power plants that burn fossil fuels to generate heat, nuclear reactors rely on a process called nuclear fission. This process, occurring deep within the reactor core, involves the splitting of atomic nuclei, releasing an immense amount of energy in the form of heat. This heat, harnessed with remarkable precision, becomes the driving force behind electricity generation. The fuel for this extraordinary process is typically uranium, a naturally occurring radioactive element. Uranium atoms, when bombarded with neutrons, undergo fission, splitting into lighter elements and releasing more neutrons in the process. This chain reaction, carefully controlled within the reactor, is the essence of nuclear power generation. Nuclear reactors are not merely static structures, they are dynamic systems, constantly monitored and regulated to ensure safe and efficient operation. Skilled engineers and technicians meticulously control the rate of fission, maintaining a delicate balance between energy production and safety protocols. Section 2. The heart of the matter. The reactor core. At the core of a nuclear reactor lies the reactor vessel, a massive steel structure containing the heart of the operation. Within this vessel, fuel rods, containing enriched uranium, are carefully arranged in a geometric pattern, forming the reactor core. These fuel rods, resembling long, slender tubes, are the epicenters of the fission process. Surrounding the fuel rods is the moderator, a substance that slows down the neutrons released during fission. This slowing down, or moderation, is crucial for sustaining the chain reaction. Water, often used as a moderator, also serves as a coolant, absorbing the intense heat generated by fission. Interspersed among the fuel rods are control rods, made of materials that absorb neutrons. These rods, acting like brakes on a car, regulate the rate of the chain reaction. By inserting or withdrawing the control rods, operators can increase or decrease the reactor's power output, ensuring it operates within safe limits. The reactor core is a marvel of engineering, designed to withstand extreme temperatures, pressures, and radiation levels. Multiple layers of safety systems, including emergency cooling systems and containment structures, are in place to prevent any potential release of radioactive materials. Section 3. A chain reaction of energy. The process of nuclear fission, occurring countless times per second within the reactor core, is a symphony of energy release. It begins when a neutron strikes a uranium atom, causing it to split into lighter elements, releasing energy and more neutrons. These newly released neutrons then go on to strike other uranium atoms, perpetuating the chain reaction. The energy released during fission manifests itself primarily as heat. This heat is absorbed by the coolant, typically water, which circulates through the reactor core, preventing it from overheating. The heated coolant then flows to a steam generator, where it transfers its heat to a separate water loop. This secondary water loop, now superheated and transformed into steam, drives a turbine. The turbine, connected to a generator, spins rapidly, converting the kinetic energy of the steam into electrical energy. This electricity, now ready for distribution, flows through power lines to homes and businesses. The chain reaction within a nuclear reactor is a carefully controlled process, with numerous safety systems in place to prevent any runaway reactions. Operators can shut down the reactor at any time by inserting the control rods, absorbing neutrons, and halting the fission process. Section 4. Harnessing the heat, from steam to electricity. The steam generated by the nuclear reactor's heat is the lifeblood of the power plant. This steam, under immense pressure, rushes towards the turbine, its blades meticulously engineered to capture the steam's kinetic energy and convert it into rotational force. The turbine, connected by a shaft to a generator, spins in unison with the flow of steam. Within the generator, a magnetic field interacts with coils of wire, inducing an electric current. This process, known as electromagnetic induction, is the fundamental principle behind electricity generation in most power plants, regardless of the energy source. The electricity generated, now at a voltage suitable for transmission, flows through a series of transformers, increasing its voltage to minimize energy loss during its journey to consumers. Power lines, acting as conduits of energy, carry the electricity across vast distances, delivering it to homes, businesses, and industries. The lights we turn on, the appliances we use, and the machines that power our modern world are all fueled by the energy harnessed from the atom's core. Nuclear power plants, operating continuously for months or even years without refueling, provide a reliable and consistent source of electricity. Their high energy output and relatively small land footprint make them an attractive option for meeting growing energy demands. Just as there are various types of engines powering different vehicles, a diverse array of nuclear reactors serves distinct purposes in energy production. Each reactor design reflects a unique approach to harnessing the atom's power. From pressurized water reactors to experimental fast breeder reactors, the world of nuclear technology is a testament to human ingenuity. Pressurized water reactors dominate, powering countless homes and industries. Their robust design and safety record make them the workhorse of the industry. Boiling water reactors offer a simpler approach to steam generation. Specialized reactors push the boundaries of nuclear technology. Fast breeder reactors hold the promise of near-limitless energy. Small modular reactors offer a flexible and scalable solution. The choice of reactor type depends on energy demand, safety, and economic considerations. Imagine a reactor where water serves as a coolant and a barrier against radiation. This is the principle behind the pressurized water reactor, or PWR, the most widely deployed nuclear reactor design. Water in the reactor core is kept at high pressure, preventing it from boiling despite the heat. At the heart of a PWR is the reactor vessel, containing the fuel rods and control rods. Water flows through the reactor core, absorbing heat from fission. This superheated water flows to a steam generator. The steam generator transfers heat to a secondary loop, generating steam. This steam drives the turbine, generating electricity. The PWR's use of two separate water loops is a crucial safety feature. In contrast to the PWR's pressurized approach, the boiling water reactor, or BWR, embraces the power of steam directly within its core. As its name suggests, water within the BWR's reactor vessel is allowed to boil, producing steam that directly drives the turbine. This simpler design eliminates the need for a separate steam generator, reducing complexity and cost. Within the BWR's reactor vessel, water flows upwards through the core, absorbing heat from the fission process. As the water heats up, it begins to boil, forming steam bubbles that rise towards the top of the vessel. This steam, now carrying the energy released from fission, is then directed towards the turbine. The BWR's direct steam cycle, while seemingly straightforward, presents unique challenges. The steam generated within the reactor core is slightly radioactive, requiring additional measures to ensure the safety of the turbine and surrounding components. However, advancements in materials science and reactor design have mitigated these concerns, making BWRs a viable and widely adopted alternative to PWRs. One notable advantage of BWRs is their ability to regulate power output by adjusting the flow rate of water through the core. Increasing the flow rate enhances cooling and increases steam production, leading to higher power output. Conversely, reducing the flow rate lowers power output, providing a flexible means of matching energy production to demand. Section 4. Breeding the future. Fast breeder reactors. Imagine a nuclear reactor that not only generates electricity, but also produces more fuel than it consumes. This is the driving force behind fast breeder reactors, or FBRs. FBRs use fast neutrons to sustain fission and breed new fissile material. Unlike conventional reactors, FBRs embrace the speed of these subatomic particles. Fast neutrons convert uranium-238 into plutonium-239, a highly efficient nuclear fuel. This process allows FBRs to utilize more energy from uranium, extending fuel lifespan. However, the use of fast neutrons and the breeding process present unique engineering challenges. FBRs require specialized coolants like liquid sodium or lead. These coolants pose handling and safety considerations, requiring meticulous design and protocols. Despite the challenges, FBRs hold immense promise for a sustainable nuclear future. Their ability to breed fuel from uranium-238 could dramatically reduce our dependence on mined uranium. Guardians of safety, emergency shutdown systems. Safety is paramount in the intricate dance of atoms within a nuclear reactor. Unforeseen circumstances require swift action to prevent hazards. Emergency shutdown systems halt the fission process instantly. Fail-safe mechanisms ensure the reactor's power can be safely reduced. These systems respond automatically to abnormal conditions. Redundancy ensures multiple systems can shut down the reactor. Constant monitoring and testing ensure reliability and effectiveness. Section 2. Neutron absorbers, the control rod strategy. The control rods, often referred to as the brakes of a nuclear reactor, play a crucial role in both normal operation and emergency shutdown procedures. These rods, made of materials that readily absorb neutrons, are strategically positioned within the reactor core, allowing operators to regulate the rate of the chain reaction with remarkable precision. Imagine these control rods as guardians of the neutron population within the reactor core. By inserting the rods further into the core, operators can absorb more neutrons, effectively slowing down the rate of fission. Conversely, withdrawing the rods allows more neutrons to interact with uranium atoms, increasing the reactor's power output. During an emergency shutdown, the control rods are rapidly inserted into the reactor core, effectively starving the chain reaction of the neutrons it needs to sustain itself. This rapid insertion, often driven by gravity or powerful springs, ensures a swift and reliable shutdown of the reactor. The material used for control rods must possess a high affinity for neutrons, readily capturing them and preventing them from participating in further fission events. Common materials include boron, cadmium, and hafnium, each chosen for its neutron-absorbing properties and its ability to withstand the harsh conditions within the reactor core. Section 3. Rapid Response Electromagnetic Actuators. Electromagnetic actuators, utilizing the power of electromagnetism, offer a faster and more controlled approach to control rod movement. Upon receiving an emergency shutdown signal, the electromagnets are deactivated, allowing the control rods to fall into the reactor core with remarkable speed and precision. Section 4, Beyond the Horizon, Passive Safety Features. These passive systems, requiring no external power or human intervention, provide an additional layer of protection, further enhancing the safety of nuclear power generation. By harnessing natural phenomena, such as gravity, convection, and thermal expansion, these systems provide an elegant and reliable means of preventing accidents. Section 1, Legacy of Power, Managing Spent Nuclear Fuel. Spent nuclear fuel, though no longer capable of sustaining a chain reaction, still harbors radioactive isotopes, requiring specialized handling and storage solutions. The management of spent nuclear fuel is not merely a technical challenge. It's a societal responsibility, ensuring the benefits of nuclear power come with an obligation to address its byproducts responsibly. Section 2, Underwater Sanctuaries, Cooling Pools and Temporary Storage. These large water-filled basins serve as the first stop on the spent fuel's journey, providing a sanctuary for their intense heat and radioactivity to subside. Cooling pools are carefully engineered environments, equipped with filtration systems and sensors to ensure the spent fuel remains safely contained. Section 3, Deep Time Solutions, Geological Repositories and Permanent Disposal. These subterranean vaults, located in stable geological formations, are designed to isolate spent fuel from the biosphere for tens of thousands of years. Geological repositories are meticulously engineered systems, designed to withstand the test of time and ensure the spent fuel remains isolated from the biosphere. Section 4, From Waste to Resource, Recycling and the Promise of New Technologies. Nuclear fuel recycling technologies aim to extract the remaining energy potential from spent fuel and minimize its long-term environmental impact. Advanced reactors, such as fast breeder reactors, can utilize spent fuel as fuel, effectively transmuting it into less radioactive isotopes while generating additional energy. Titans of energy, unveiling the world's most powerful nuclear plants. These colossal structures, often spanning vast areas and housing multiple reactor units, hum with an invisible energy, their turbines tirelessly spinning to illuminate our world. Join us as we explore these titans of energy, delving into their history, design, and impact on the global energy landscape. A global tapestry of power. Kashiwazaki Kariwa, Bruce, and Zaporizhzhia. Kashiwazaki Kariwa in Japan, Bruce in Canada, and Zaporizhzhia in Ukraine represent the world's most powerful nuclear plants, each with unique contributions to their nation's energy portfolio. These plants highlight the diverse ways in which nuclear power is shaping the world. A legacy of progress. Enhancing safety, embracing innovation. The reactors of today are embodiments of decades of research, development, and a commitment to ensuring the power of the atom is harnessed responsibly. Digital monitoring systems, powered by artificial intelligence, provide operators with real-time insights, ensuring the safe and reliable operation of these powerhouses of energy. Fusion Horizon, a glimpse into the future of energy. Imagine a future where the world's energy needs are met by fusing atoms, mimicking the cosmic dance of energy creation that has illuminated the universe for billions of years. The allure of a future powered by the stars continues to drive researchers forward, unlocking the secrets to a truly sustainable energy future.